Otterbein University, Westerville, Ohio, is a small private liberal arts university founded in 1847 and has a strong emphasis on STEM, the health sciences and business. Their first systems engineering class started in 2015, followed by a mechanical engineering class in 2017, with a total of 117 graduates across the two programs currently. The Point, completed in 2018, is home to the Department of Engineering, Computer Science and Physics offices, laboratories and classrooms, as well as a number of corporate partners, and also houses a state-of-the-art makerspace.
Hi, my name is Dan Mendelson. I'm a professor in the Department of Engineering, Computer Science and Physics at Otterbein University, and I'd like to welcome you to our Thermal Sciences lab. I've been teaching for over 40 years, but almost all of that has been lecture courses. But in the past 5 years here at Otterbein, I've had the opportunity to set up, develop, and purchase equipment for two labs. One, our Thermodynamics lab, and the other, this Thermofluid Sciences lab. Our curriculum consists of a full course in thermodynamics in the lab, a full course in fluid mechanics, and a full course in heat transfer, and this lab supports all three subject areas. The TQ equipment has been essential in setting up this lab. We have the two hydraulic benches here. We also have the heat transfer equipment too. The manuals were great, easy to set up, easy to use. It's been absolutely essential in setting up this particular laboratory. So let's talk a little bit about the equipment we're going to show today. We want to focus on the TQH13 Vortex apparatus. That is one of several experiments that sits on top of the hydraulic bench, the TQH1F hydraulic bench. The bench is simple. It's a tank of water with a pump and a readout. Flow rate is controlled just by the valve here. Okay, the pump is a constant displacement pump, but not the same all the time. The TQH13 Vortex apparatus, let's go over the parts of that. There's this outer cylinder that sits on this base, and that can be rotated by this motor. In one experiment, we plug the drain here, fill the compartment up halfway, spin it, and create what's called a force vortex. We get a bowl, a nice bowl here. Okay, and in the other experiment, we'll take this inner cylinder and put it in here, and open the drain. It'll drain out. We'll supply here so to keep the same volume of water, about the same volume of water all the time, and we'll spin this too. And that'll create a free vortex. It looks like water going down your drain in a bathtub, except we're spinning it a little faster here. Crossbar here sits on top, has to be level, so keep a level around, check that level all the time. And then this bracket here is moved to different positions where you measure two different things. You measure the surface profile using this rule pointer here. Just touch the surface and measure where it is. And we have this Pitot tube right here, which we can put into the flow, and that'll push water up into this tube here, and that'll measure what's called the head, the energy of the flow. So why do we do this? Why do we study vortices? Vortices occur in nature all the time. Tornadoes, hurricanes, oceanic flows, blood flow in your veins can end up being vortices. We get vortices around all aerodynamic structures, so off of the tips of cars, airfoils, wings, etc., and even in standard pipe flow and lots of mechanical engineering devices, you can end up with a vortex. In general, they're undesirable, especially hurricanes and tornadoes. And we like to understand them and be able to predict how they behave. So this experiment goes after that. We theoretically predict the shapes of these profiles and the head as well, and we compare the experimental results to that.